So our speaker is a best-selling author of both fiction and nonfiction. Lee Gruenfeld has spoken on such topics as computer law, language, and futuristic computing technologies. He's been a columnist and feature writer for Computer World, the science and technology columnist for Newsmax, and writer and photographer for Ironman.com, the official website of the World Triathlon Corporation. He's been a long-time old bull pilot, so without further ado, Lee's going to talk to us about GPS today.
Oh, okay. I'll take that, yeah. That's the word, okay. Jackson, I'm really glad you're here because that makes you the only guy in this room with fewer flight hours than me. So welcome again. I haven't spoken to you for a few months. We're going to talk about GPS and something that we all use. I'm not sure that everybody quite understands what a real miracle it is, but that's what we're going to talk about today. And I have a tendency to take the mic away from my mouth to just make obscene gestures toward me, and I'll fix it. I'm very fascinated by technologies that fade quickly and are out of date very soon. Not to say too much about Max, but he's the first guy that saw this today and said, "Oh, that's a Gruenfeld, isn't it?" Yeah, okay, that's a slide rule, a real one. But you know, as an example, phonographs. You know, if you take a look at the top row, the evolution, even though they got better, they're still nothing more than needle scratching grooves in vinyl. And then all of a sudden, there was this revolution, double revolution. We digitized sound, which was pretty amazing. Figured out a new way to store it. That was the miracle. It lasted a couple of years, and now you don't need any of that stuff because you have an iPhone. All of these things are obsolete. You just don't need any of them anymore. And
as long as you don't have pictures of pilots up there.
Yeah, that's true. No, I don't. And all of these things, one of the great technological revolutions, you can throw all that stuff away. Everything's in the iPhone. So we're going to talk about another revolution today in navigation, which is similar. And in order to talk about it, we're going to have to kind of go back in time a little bit to understand what the actual problem is. We're going back a couple of hundred years. So buckle in, we're going to be here for a while. Whoops. So in 1707, a British war captain, was coming back to England with his ships, heading for a safe port in New England. And a young officer got up on the deck and said, "Hey, Captain, I think you made a mistake. I don't think we're anywhere near the port. We're heading for the Scilly Islands." Captain had him hanged on the spot because you don't do that in the British Navy. That's insubordination. And 2 days later, they crashed into the rocks on Scilly Island. They lost 4 ships, close to 2,000 men. It was the worst marine disaster in British history up until that time. And why did this happen? And it's not an isolated incident. Anybody recognize that bell? It's called, huh?
Lloyd's Fund.
Yes, exactly. It's called a lupine bell. And at Lloyd's of London, the biggest marine insurer in the world, every time they lost a ship, they'd ring the bell. And by the early part of the 18th century, this thing was going off like a pinball machine. They were losing so much, losing hundreds of thousands and thousands of men, billions of dollars, current dollars worth of cargo. And why were they doing that? They were doing that because why were ships being lost at sea? Because they were literally lost at sea. And the whole problem boils down to one word, which is longitude. So, longitude was so difficult or impossible to determine that a few years after the Scilly disaster, the British government created became known as the Longitude Act. And they offered a whopping prize, like millions and millions of equivalent dollars for anybody who can figure out how to find longitude. So to understand why that's a problem, let's talk about latitude, obviously. Latitude is easy. Latitude is a natural result of the astronomical configuration between the Earth and the sun. It's really quite simple. You don't have to create an artificial equator. It's the 90-degree circle parallel to the spin axis of any turning object. And to find it is really easy. You wait until high noon, which is easy to figure out with a double mirror astrolabe, and then you look at the sun. If the sun's directly overhead, you're on the equator. If the sun's halfway down, you're at 45 degrees, one way or the other. If it's a little sliver on the horizon, you're at one of the poles. And it's very simple to do. This is an old machine that was recovered. You sight through the holes. It's got a couple of drop needles that will simply tell you what your elevation is. And that's really simple. Now, this guy, I've always wondered why pirates tend to have eye patches. Why are they only getting shot in the eye? Why their nose is not getting shot, or the ears or something? And come to find out that when you see a pirate with an eye patch, he was probably a navigator who has been staring into the sun for years and years and years in order to determine position, got his eye burned out over time, and that's why so many pirates wear eye patches. Little fun fact for you there. And of course, there's one little adjustment we have to make. The Earth doesn't turn perfectly level. It precesses, like if you've ever seen a little toy gyroscope wind down and it wobbles. Well, the Earth does that too. Once a year, one cycle, which is why we have seasons, but it's also very well known, very precisely determined. So what you have is a little chart, can fit on a couple of pages. And when you look at the sun, you look at the chart and you say, oh, it's March 13th. I need to subtract 12 degrees. We've been finding latitude without problems for many, many years. Longitude, this is a different problem altogether. And part of the problem with longitude is that it's not a natural consequence of anything. Unlike the equator or the poles, there's no fixed reference for longitude. So at one point, the British said, well, let's draw a line from the North Pole to the South Pole. We'll pass it right through the observatory in Greenwich. That's the prime meridian. Let's call that 0. But it didn't have to be there. The prime meridian has gone through Rome. It's gone through Paris. It's gone through Philadelphia. So there's no natural prime meridian, which is part of the problem. So when they offered this prize, they put it in the hands of the Royal Society, which was dominated by astronomers, and they decided they're going to figure out how to do this with star charts. And a lot of guys spent a lot of years making extremely detailed observations of the nighttime heavens, very sophisticated stuff. They used eclipses of the moons of Jupiter as references. It took them years and years and years. They produced almanacs that were this thick, updated them every year as their observations got finer, and it kind of worked. If you had a PhD in this stuff, it took 4 hours to take a reading, and then it only got you within 50 or 60 miles of longitude, which for some purposes was fine, but it really wasn't enough. But the astronomers were bound and determined that this was the way to go. However, there was another idea floating around, which is using clocks to determine your longitude. So think about this. The Earth rotates once a day through 360 degrees, 24 hours. So every hour of rotation is 15 degrees of longitude, regardless of where it is that you started. So this becomes really simple. You take your boat to Greenwich, you wait till noon, you hear the bell, you set your ship's clock to Greenwich time, and then you head out to sea. When you're out at sea, you find noon. Easy. We already know how to do that with latitude. And you say, oh, it's noon here. You look at the clock. Hey, it's 1 o'clock in Greenwich. I'm 15 degrees away. Very, very simple. Okay. So you just multiply the difference by 15 degrees. And bada bing, you got longitude. What could be easier? One little problem with that ship's clock. This is what a clock looked like until the middle of the 18th century. This is what a clock looked like after 20 minutes at sea. And even if you don't break the clock, pendulum clocks just don't work on rocking, rolling, storm-tossed boats with different changes in temperature and humidity thrown in. So that really wasn't going to work, and it was abandoned. Then a guy named John Gregory Harrison came along. He spent 20 years trying to build a clock that would work on a ship. And he came up with this. This is called H1. It was the first Harrison clock. A miracle of modern engineering. He used metals of different coefficients of expansion in order to reduce the effects of temperature, swinging counterweights, and most importantly, it used springs instead of pendulums. This was amazing. But the astronomers were very distrustful of it. Whoops, sorry. They sent this thing out on multiple voyages for years, kept claiming that there were problems. So Harrison built H2 and he built H3, and it got better and better I'm going to shorten this story a whole lot until he finally came up with this thing, H4. And if you rank the great inventions of history, this one is in the top 10. It solved the longitude problem. It looks like a pocket watch. It's actually about this big around, weighs 3.5 pounds, has 728 moving parts. Temperature, humidity, shaking the watch made no difference at all. One of the problems with previous spring-mounted clocks is that the weaker the spring wound down, the slower it went. This one either was keeping time or it stopped dead. And, which was really unusual, is while you wind it, it keeps on going, and other clocks couldn't do that. Most importantly, and this is amazing for a mechanical device, didn't lose or gain more than a second per week. This won the prize, and the longitude problem was solved. Shipwrecks absolutely plummeted. If you take a look at the chart, it's really quite amazing. By the way, anybody know what this is called? It's a trick question. No, it's not. It's just, huh? Marine chronometer. That's what a marine chronometer is, and that was the very first one. Well done. Okay. And since then, obviously, navigation has evolved. By the way, land navigation is easy. NDBs, fixed radio signals, VORs, things like that. Not a big deal. The device in the middle left is LORAN, if you remember that, long-range navigation on the sea, charts. And then we have inertial navigation devices, which were pretty amazing, that detected the motions of the planes and then inferred speed and position from that. They started out as mechanical on the lower left, moderately complex. Gyroscope spinning in all three planes, and then we wound up with ring laser gyros, which have no moving parts and are incredibly accurate. Both of these, though, are prone to drift over time. Which brings us, finally, to GPS, which is what we're going to talk about today. I just wanted to give you a flavor for the problem we were trying to solve with this. So, GPS, and this is what this talk is really all about, is to appreciate what's really going on here. It sounds like a simple triangulation problem. As you know, if you're wherever you are, if you can get your distance to 3 fixed reference points on the ground, you know precisely where you are. That's triangulation. Okay? GPS uses something called trilateration. It works in 3-dimensional space instead of a 2-dimensional surface. And instead of using circles, it uses spheres. Now, I couldn't help this. I had to throw in a picture of the sphere in Vegas, which is my new favorite place in the world. So let's see how that works. First, you got to ask yourself, how far am I from a satellite? Well, it sounds simple enough. You send a signal up to the satellite. I'll show you this picture. You know what these things are? Golfers, hunters, right? It's a rangefinder, laser rangefinder. Shoots out a laser range, comes back, measures the time difference, and gives you a pretty good, within a yard or two distance. So it's a common belief that the way the GPS works is that your phone or something shoots a signal up to the satellite, measures it coming back, and that's absolutely not how it works. And there's a couple of reasons for that. First of all, there are a lot of GPS devices in the world. Okay? They track somewhere between 1 and 5 times per second. They use at least a half a dozen satellite, which means they're pinging satellites 50 billion times a second. And there's no hardware or software in the world that can process that, not to mention sending back 50 million signals individually coded to 50 billion different devices doesn't work. On top of that, these satellites are about 12,000 miles high. So in order to power such a device, you would need to carry around a 20-pound lithium battery, which not incidentally would fry your brain every time you used it. So this ping and return method doesn't work. So the important thing to remember about GPS is that they are receivers only. They don't transmit anything. And what happens is that the satellite is constantly sending out what's called a PRN, a pseudo-random number that contains its location and its speed, and most importantly, the time at which the signal was sent. And it does this about 10 times a second. It comes down to your GPS device, and the phone says, hey, I just got a message from this satellite saying it's 1 o'clock and so many nanoseconds, but my time is different. The difference between those two times multiplied by the speed of light gives you the distance to the satellite. Okay, that's how it's done. So once we know the distance to the satellite, now we can construct the sphere. The radius is the distance, and I've got this great big sphere, and this narrows it down to somewhere within 1 billion square miles. It actually, the calculation comes out to 2 billion, but since we're on the ground, half the sphere is below us, we can throw that out. So now we got it down to 1 billion square miles. So what do we do next? We take a second satellite. Now we got 2 spheres. Where 2 spheres intersect, it forms a circle. So now we're getting a lot more accurate with somewhere between 10 and 70,000 miles of where we are, working it down. So the next thing we do, we take a third satellite, and that gets us down to 2 points. We can only be at one of 2 points. Trick question. How do we figure out which point we're on? Anybody? I knew somebody was going to say fourth satellite. No. It's very simple. One of those points is on the ground and one's in space. You pick the one that's on the ground, or if you're in a plane a couple of miles above it. Very simple problem. And now you know where you are. So why do we need 4 satellites for an accurate fix? This is a tough one. This is what timing errors amount to, okay? If you're off by 1 billionth of a second, you're out of whack by a foot, which to you and me doesn't make a lot of difference, but to a surveyor, it makes a whole lot of difference because those guys have to be accurate down to the inch. Okay, if you're 10 nanoseconds out, you're still 10 feet out. If you're 1/millionth of a second, that's 1,000 feet. So we need an awful lot of accuracy out of our GPS system. Problem is, here's your iPhone. Its clock is only accurate to within 50 milliseconds. Okay, which means you can be as much over 9,000 miles out of whack if you rely on that iPhone. The purpose of the 4th satellite is to resolve those timing differences. And this should be self-explanatory, so I'll let you read that. This is how it's done. These are 2 out of about 600 paragraphs describing how to do that timing discrepancy in the GPS specs. Okay, everybody got it? Good. All right, so I'll just jump through that. So now we know where we are. And that's the end of the problem, right? What could possibly go wrong now? Well, it turns out an awful lot of stuff can go wrong. To start with, the orbits of the satellites are not really fixed. You think from your old physics classes, if you've got an object falling through a vacuum unimpeded, you can tell exactly where it is at all times. But there are a couple of problems with that. First of all, the Earth isn't round. This is an exaggerated drawing, but the Earth is an oblate spheroid, slightly flattened sphere. It bulges at the equator because of centrifugal forces, and the bulge is significant. There's a 26-mile difference between the Earth's diameter across the equator and through the poles. And this wreaks havoc on satellite orbits and has to be resolved. Second of all, we're not the only gravitational field that's acting on those satellites. We've got the moon, we've got the sun. And then there are tidal forces. The moon, the Earth, and the sun are not points of gravity. They're great big spheres of gravity. And the pull is stronger on one side than the other, which is why we have tides. And you've got to take that into account. Then there's solar radiation. Does anybody remember this little toy? I think it's called a Crookes radiometer, but I'm not really sure. It's got vanes with black on one side, white on the other. It's inside a vacuum. You shine a flashlight on it and it starts to spin because light applies pressure. Well, imagine the naked sun shining on a satellite, shoves it around all over the place. And then there's radiation pressure from the Earth, albedo, which is essentially reflected light like off the poles and ice caps and things like that. And the Earth sheds heat. The satellite itself re-radiates heat. It's got maneuvering engines on board, gas leaks. It shoves the satellite around. And this one, I couldn't believe. I just discovered this one. When it sends out signals, the pressure of sending out a radio signal will actually put a little tug on the satellite. It's not much, but it matters. And then, of course, sometimes we boost these things up to higher orbits or adjust their orbits. So there's some other things. So how do we resolve all these orbital differences? We do it with something called an ephemeris database. There are two master control stations for GPS. They're both in California. There are monitors and ground antennas all over the place. And these things are constantly monitoring the satellites, creating a database of ephemeris, which means the trajectory, the speed, and the location of every satellite. And about once an hour, it uploads all of this to all the satellites. So they all know where they are in relation to the reference stations and where they are in relation to all the other satellites. And that takes care of those perturbations. We got other problems. We think that light moves at 186,000 miles per second, or 300 kilometers per thousand kilometers. That's only in a pure vacuum. There's a lot more than a pure vacuum between the satellites and the Earth. For one thing, we have the ionosphere, which is called ionosphere because it's got a lot of ions in it. And it severely affects the signal coming back. So they have to resolve this using two receivers on the ground with two different frequencies coming out of the satellite. Then you have tropospheric delay. We have different temperatures, pressures, humidity. This is one of the equations that they use to model what the atmosphere looks like. Everybody got it? Okay. There's a mistake in there. See if you can find it. And here's my favorite. I saved this for last because I love this one. I will just tell you that if you'd put this system up before 1917, it wouldn't work because of this guy. And here's the reason why. We have something called time dilation, relativistic time dilation. As things speed up, time slows down, it changes. And this looks like a daunting formula, but it's actually very, very easy, okay? So the new time is equal to the original time. Oh, I'm sorry. So V is your velocity, C is the velocity of light. So what happens if you're standing still? What's V? Zero. Okay, what's 0 over c squared? Zero. What's 1 minus 0? What's the square root of 1? What's the original time over 1? Is the same as the new time. If you're standing still, there's no time dilation. But as you speed up, that bottom number gets a little smaller, the top number increases, which is your speed relative to the thing that's moving. We have to worry about this. On the other hand, we got another problem, where as gravity weakens, time speeds up, or I should say gravity slows time down, which is the opposite problem when you have a satellite out in space from its speed. So you put those two things together and general relativity results in the clock speeding up about 45,000 nanoseconds, which is a lot. The high velocity slows it down. The net adjustment is 38,000 nanoseconds. And remember, 1 nanosecond is a foot. If you don't do this, you got a 5-mile error. This is all about relativity. And these relativistic time dilation equations are built right into the GPS software. Actually, the hardware, they slow the clocks down specifically. Okay? Oh, yeah, and in case you think this is theory, it really isn't. During the Apollo missions, they took an atomic clock, 2 atomic clocks, synchronized them on Earth, put one up in the satellite, in the spaceship. It zoomed around the Earth for a couple of weeks, and when it came back, the clock on the Apollo was 22 millionths of a second behind the one on the ground, which is precisely what relativity predicted. So that's very, very real. Okay, just a couple of more. I thank Bob Lilac for this. I was not aware of this. I thought GPS was as good as it gets. How can you possibly have a better system than GPS? It's accurate to within a centimeter, which is about 1/3 of an inch. It's just fantastic. The military is starting to get worried because you can jam satellites and you can spoof them, meaning putting out spurious or false signals. And so they're experimenting with something called optically pumped magnetometer. Yeah, I know. They use a device called a SQUID, superconducting quantum interference device, which is insanely sensitive to magnetic fields. And it turns out the magnetic field of the Earth varies from square foot to square foot. And so if you can map that and you can have a completely self-contained unit that can detect it, you can't jam it. You can destroy it, but you can't, there's no way to jam it. And it's not dependent on any signals going in or out. I have my doubts about this thing, but they're experimenting with it now. So we got a couple of challenges. It's hard to make those maps quantum devices are supremely sensitive to noise, which is the difficulty with quantum computers. And so you got to harden the devices against all this stuff. Okay. One last thing, another fun fact. It doesn't start off so funny, but in 1983, a Korean airline passenger jet wandered into Soviet airspace. Soviets said it was a spy plane. There was actually some evidence for that, but basically it just got lost. And they shot it down. All the people died, including a US congressman. So I should have mentioned, up until this point, GPS was just for military use. So a couple of guys wrote a memo saying, why don't you open this up for airline use so we can stop this kind of problem? And Ronald Reagan did it in 1983. He opened it for civilian use. The two guys who wrote this paper, one of them was Ollie North. Does that sound familiar? And the other one, anybody want to guess who this is? You'll never guess this. But if you use GPS and you appreciate it, say thank you to Bob Lilac on the way out. He was on the Ronald Reagan's National Security Council staffer, and he's one of the guys that got this opened up. So that's it. That's everything I know about GPS. So I probably can't answer any questions, but I'll take them anyway. I think that's.
Who's got questions?
Uh-oh.
That was really informative for
Thank you.
somebody that had never figured out a GPS. It might as well be Chinese to me. And I was ferrying a float plane up to Alaska 10 or 12 years ago. I was out flying with my buddy the night before in Vancouver, seeing how the airplane flew because I'd never flown it on floats before, and I was heading to Fairbanks the next day. And he handed me ForeFlight. And he says, forget the GPS, throw those stupid maps away. And I go, well, I got maps. I use maps. I don't trust GPS because battery goes dead. I don't have the right plug-in or something. Like heading to Alaska with the ForeFlight, that is probably the greatest invention that for a guy like me could ever have in his hand. It's in my phone. I mean, it's unbelievable. Just throw the GPSs out that you carry around the plane. I've never used a tool like it, but so this is another Alaskan story. So about 20 years ago, maybe even 15 years ago, we were having a rash of aviation accidents with single engine bush planes. And there was 20 or 30 fatal accidents, guys following terrain with their GPSs. And they were flying into the mountains in bad weather and, trying to go through these passes. And it was determined that the information used in Alaska came off of some very unreliable sectional maps.
Mm-hmm.
And I could never understand. I mean, GPS seems like it's absolute, but it was, and what I had read, that they needed to map the state of Alaska properly to these passes were 500 feet in elevation off because they'd been done by sextants and horseback back in the 40s. And the elevations were off, the passes were off by a quarter mile. I mean, how does this relate to GPS? I could never understand how it could be so screwed up.
Yeah.
Can you explain that?
Well, sort of. The original GPS used various terrestrial measures. The mapping is all done by satellites now, and it's extremely accurate. They use radar beams to bounce off. And I don't know if they have accurately mapped every spot on the planet Earth on land. You don't care about the ocean on land, but that it's done using satellites now.
They wanted funding from Congress to fix the map in Alaska. And my buddies were flying a fuel plane one night, about a Kenai around. And it's dark, 6,000 gallons of diesel on board, and 4 inches DC6. They're going over the Alaska range in the dark. And they got this weird buffet at this one location. So about 4 hours later, they're doing it again. making another round to Indian Mountain, same spot, whole airplane just shuddered. Well, about 2 days later, they're doing it in the daylight using the GPS, and they were within 100 feet of the mountaintop.
When was this?
15 years ago.
Yeah, imagine it's gotten better since then, I hope.
Well, I don't know. I mean,
I don't know.
Yeah, I don't know. Right, yeah.
I mean, you shot GPS approaches into Alaska, right? But that's airports and known jetways and things like that, I
Yeah.
guess.
Got to be careful on your database, what everything is plugged in.
Yeah, true.
Other questions? Must be other questions.
Since Lee stuck my name up there, I just make a comment about what happened with President Reagan. You remember the airliner story? The airliner took off from Anchorage, and I think he really wasn't flying by any of Dan Gilbertson's rules. He screwed up when he took off. They did not put in the wrong coordinates. He took off. Supposedly, the airliner was flying in heading hold rather than nav mode. By the
Right.
time they figured out where they were, what they were doing wrong, they put it back in nav mode, and they wound up flying by mistake over the Kamchatka Peninsula. And that's when the Soviets decided to shoot it down. They thought it was one of our RC-135s doing spy work. That was proved wrong by some of the intelligence that we had. And Reagan just said, why the hell did those pilots just fly in the wrong place? And the answer was, we explained what really happened in that particular case. And the only solution that we had that we could offer was in fact GPS. GPS wasn't fully developed yet. This was 83, it didn't get developed. GPS, as Lee would know, really went into operational use in 1988. And when it was released with a little bit of an error. So we didn't really give the civilians as much accuracy as the military had. That was corrected in 2000. And now you've got it down in your phone. So you can thank, actually, not necessarily thank President Reagan, but you can thank the Soviets because they shot down the airliner, which led us to this. It probably would have happened anyway, but this triggered it.
You know, those are great big uses for GPS. My favorite is this. I bought the very, very first handheld GPS that came out. It cost about $1,700. It was, kind of sort of accurate, but it had a button on it labeled MOB, and it was man overboard. If you were on a ship and somebody fell overboard, you just immediately hit that button and it took a fix. And then later you press another button that would take you back to it. Now, why did I need that? Because of water skiing. I like to ski on one ski, but I can't get up on one ski. So I get up on two, drop one, and we're all over the lake, and now I've got to go find this ski. Well, my buddy hit the MOB button when I dropped the ski, and that $1,700 device helped us save an $80 ski. That was my use.
All right, any other questions?
Okay, thank you all for showing up.
Thank you, Ms. Grant.